Yep. Okay, finally. Woohoo! We can process terabytes and petabytes of data, but still can't get a laptop to plug and play. Yeah, technology. Anyways, finally, so I am TD. Uh, that's my initials, and I'm essentially a core committer of Spark, and I'm the lead developer in Spark Streaming. So you will probably find most of my commits going into Spark Streaming, and I'm on leave currently on from the PhD program in UC Berkeley. Okay, so let me start with a very brief history of why we built, of what is Spark Streaming, the what and the why. And it's essentially, just like Spark SQL, it's essentially an extension of the Spark API. It started as a research project back in 2012, where we started building this thing. And for building this thing, we actually took Spark, the existing version of Spark, and tore out all the internals of Spark to make it 10 times faster than what it was back then. And we released the first version of it in early 2013 and as an alpha, and then early 2014 it graduated with Spark 0.9. It graduated as a non-alpha full-time thing. So why did we build it? Now, back in 2012, we started looking around and asked people Spark what more do they need from Spark, and also generally looked around, and we found that there are lots of applications out there which actually want to process data in real time. As in, there's data coming in from live data sources, and you want to get results from that data as soon as possible. For example, you want to monitor your websites or a set of websites or your sensor nodes, etc., and figure out whether they're working properly or not. There's no point if you get to know that 1 hour later after you've run your Hadoop jobs and stuff, because the harm is already done. Similarly, you want to do fraud detection as soon as the fraud happens. You want to do GAD monetization, change stuff as soon as things are happening. So for this kind of stuff, the common theme across all of this is that there was a need for a distributed stream processing system that can receive all these data streams and convert that data into value in real time. And for that, obviously, you need the system to be scalable to hundreds of nodes, as well as achieve low latency. And we found that a latency of the order of seconds covers a lot, probably around 90% of the most use cases that people were asking for. Additionally, we also found that it's important to deal with failures. If you're working in a cluster environment, you're probably going to have your worker nodes failing and stuff. A stream processing system needs to recover efficiently from failures while giving guarantees on what the result of the data is despite of failures. And another important fact that we found is that it should integrate well with batch processing and stream processing, batch processing and interactive processing systems. Let me elaborate that. Why is that the case? So we asked many companies, and we found that many such environments in data processing environments in companies actually have the requirement that the same data that they are going to process in real time, they're also going to do post-processing on that data offline. For example, you want to process the same data and generate monthly reports, yearly reports. So for that, the same data needs to be processed in two different scenarios. One, real time, as well as a larger volume of data in offline. Now, there doesn't or exist any framework that could do both together. For both process terabytes, petabytes of data over large volumes of data with, let's say, low latency hours, as well as do hundreds of megabytes per second with low latency stream processing. So the way people dealt with in the existing technology was that people built two different stacks. One, a Hadoop stack or equivalent stack, which used to process terabytes, petabytes of data, the other, the real time. Now, the problem with this dual stack model is that you have to express your computation in two different models. You have to deal with these two different programming models, two different execution models. You have to deal with two different kinds of bugs. You have to deal with, from operational point of view, you have to deal with two different stacks completely, which is a huge headache. So we thought of simplifying it. Another challenge is that achieving fault tolerance in a streaming environment is actually not that easy. It's actually a hard technical challenge. For example, the way traditionally stream processing has been done is using this model where you have a worker of nodes with a streaming pipeline set up between these workers, where every worker is doing one computation. Let's say a worker is supposed to filter the stream and forward it to the next worker. Now, if you want to do something like a running count of how many records the stream has seen, the way it is done is you have a mutable state in the memory of the worker. There is basically a counter, which the counter is incremented every time a record is forwarded to the next node. That's how people have been doing it in traditionally. But the problem with this model is that the moment the worker dies, that counter in the memory is lost. And so you might suddenly find your count of the number of records received till now suddenly 0, which is not good. And dealing with this kind of idiosyncrasies is really a hard challenge. And so making stream processing fault tolerant is actually is actually an academic challenge, which motivated us to actually take up this research project, and thus we created Spark Streaming. Now, just to give you an example of how other systems deal with this, for example, you might have heard of this popular system called Storm. The guarantees that Storm gives is that it will process every record at least once. So it is not exactly once. So what may happen is that if you're counting your records, you might easily get double counted. And in practice, it actually happens so. And again, if you are maintaining any arbitrary mutable state, your node dies, your state is gone. And so real systems actually have these problems. As a follow-up to Storm, there was another system written on top of it, Storm, called Trident, which uses transactions to update this mutable state to make sure to get the exactly once processing model. But what we have heard from many developers is that this per state transactions actually causes a huge impact on throughput. So many developers actually don't use this Trident to achieve the throughput they desire. So we ended up building Spark Streaming. And the idea behind Spark Streaming is actually very simple. You take a streaming computation and express it as a sequence of very small deterministic batch jobs. So you have your data stream coming in. What Spark Streaming will do is that it will divide your data stream into batches of X seconds. Now this X is configurable by the developer. Once it divides the data stream into batches of X seconds, it actually forwards those batches of data to Spark. Spark processes that and gives out the results also in batches. And with this very high-level model, now the real technical challenge is to allow this sort of batched processing at a very low latency of the order of seconds. And this was not exactly possible to do of the order of seconds in other existing systems. Like you could, at a high level, you could use this model in Hadoop, but you probably will not be able to do it in the order of seconds. You'll probably be able to do it, say, 10 minutes at the best. So but in Spark and Spark Streaming, we can do it because Spark is a really, really fast processing engine, which allows jobs to be run in the order of milliseconds, which allows us to process data in the order of seconds, which allowed us to build Spark Streaming on top of Spark. And also, an additional advantage is that since it's built on this batch processing platform, we expect it to be much easier to integrate batch and stream processing together in the same place. So you have already heard about RDDs from Reynolds talk. In Spark Streaming, we provide an additional abstraction over RDD, and it's called DStream, which is the short for discretized streams. And the idea is that a DStream is essentially a sequence of RDDs representing a stream of data. Now, this DStream can either be created from your input data source or by transforming other existing DStreams. It's kind of similar to how the RDD model works, where you can either create an RDD from a Hadoop file or by transforming other RDDs. So let's see it in action, how a streaming program looks like. So similar to a Spark program with a Spark context, you have to first create something called a streaming context, where you specify what is the batch size that you're going to use. In this case, we are using 1 second. And to create a streaming context, you need a Spark context as well. So I'm assuming that that has already been created. So once you create a streaming context, that gives you access to these library of utilities that allows you to create new input stream from different sources. In this case, let's say, since I want to count hashtags or get the hashtags from Twitter, we're going to use Twitter util to create a Twitter DStream, which essentially creates a new input DStream. And what happens underneath is that as data is received from the Twitter streaming API, the data is chunked into batches, and the batches of data is stored in Spark's workers' memory as RDDs. Next, we want to do some transformation over these tweets. Let's say we want to get the hashtags out of it. So for that, we apply this transformation flat map to get the multiple hashtags from each of the tweet. And this transformation essentially creates a new DStream. And underneath what the system, when you run this whole program, what the system would do is for every batch of data that is received, it will do these flat map operation on that RDD underneath and create new RDDs. And this new sequence of RDDs will essentially form the new DStream. By the way, feel free to ask questions. I'm happy to have this session interactive. Yes, back. Sorry? So I don't have a demo plan for this session right now. So the way, let me just add on to this, and that may probably answer your question. And finally, once you have done all your data transformations, you're going to do something with the data, maybe push it out to HDFS. Let's say for that we have this operation called save as Hadoop files, which saves each bat of processed data, in this case hashtags, to as Hadoop files. And these type of operations are called output operations. And it's not just saving to, what it essentially does is saving to HDFS. And not just saving as HDFS, you can do arbitrary stuff with the transformed data using this operation called for each RDD, which gives you directly access to the RDD. And you can do whatever you want in that. Either push it out to some external database, let's say Cassandra. You can directly push it out to a dashboard website to update your dashboard, whatever you want. Now, the way this lazy, okay, yeah, sure. I can barely see. Oh, there you are. Yes, exactly. So to reduce the latency, you want to be able to process things in smaller batches. The smaller the batch, yeah. No, that's not true. So if you have, I mean, these are two independent parameters: the batch size and the size of the cluster. Yes. Yes. So the question was that if your batch size is small, does it mean it's better to have a smaller cluster? Is that, I'm guessing that's the question, is it? Okay. I could barely hear. Thanks. If you want to reduce latency, does it benefit from adding nodes to your cluster? Yes, absolutely right. So the more nodes the cluster, the more parallelism that you can take advantage of, the faster you can process, the lower the latency you can achieve by reducing the processing things faster. Even if the batch size is small, you can process things faster with a larger cluster. Yes. Um, and so, and and the way this streaming program works is that this all this similar to the Spark's philosophy, all this computation is actually lazy. So while the system is executing these commands on the screen, no operation is happening. You need to finally do streaming context dot start for the computation to actually start. And you're going to see that in action in your tutorial itself, so you'll get a sense of how this works in actions. Moving on. So you can write this computation in both Scala and Java, and the Python API is in the works. It will come soon. And for Java, you obviously have to use these function objects rather than the simple Scala API. What you get along with these DStreams is, yeah, questions. So when I do saying save as Hadoop files, so the question is that when I use save as Hadoop files, what exactly is being saved? So if you see the example carefully, I'm calling hashtags.save as Hadoop files. Okay, so hashtags is essentially the DStream that contains all the hashtags that are being received, right? Uh, so each batch of hashtags is going to be saved as a different file. Yes. Yes. So using it, yeah, yeah. Each batch of hashtags will be written to a different file. So you open the file, close the file. Yes, 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 yes. So yes, it's not recommended. So this is just an example. It's not entirely recommended to do this really at a very low latency. So typically what people use is save as Hadoop file with and use that to actually write it to Cassandra and use the same API to write it to Cassandra, in which case it is, which works pretty well. So what question was what formats are supported through this? So we are using the Spark's underlying API for writing to arbitrary Hadoop files. So whatever input format or output format is supported through HDFS API, it is, yeah, all that is supported through this. One last question before I move on. Mm-hmm. Yes, so the question was whether the data in these small RDDs in the batches are partitioned or not. Yes, absolutely. Yeah. Moving on. So what you also get out of these transformations, out of the DStream API, are window-based transformations where you can specify that give me the data over the last, let's say, 1 minute, and move the window every 5 seconds, let's say. So so what happens underneath is essentially the sliding window that operates on the DStream. And you can, and this window is operation is defined based on two parameters. One is the length of the window, in this case 1 minute, and second, the how frequently does the window move. So in which case it is, in this case it is 5 seconds. I can barely see the screen on my system, which is why I'm having to peek at the big screen. Anyway, better. Okay. Now, using this window operation, you can do a lot of complex event processing type operations within the DStream itself, and there are multiple flavors of this window operations. You can do reduce by window, reduce by key and window, and all these different flavors of window operations are there. You can look up the Spark streaming docs for that. Also, you can do arbitrary stateful computations where you can specify that for any key, you want to maintain a continuous state that you want to continuously update as data comes in. To take a very slightly weird example, where let's say you want to monitor Twitter, and for every user in the Twitterverse, you want to maintain what mood the user is in. I know it sounds creepy, but let's say to do that, all you need to do is essentially define this function called update mood, where given the previous state or the of the user and the new tweets from that user, you can calculate the new mood the user is in. And once you have defined this function, you can use that function in this DStream operation called update state by key, where you apply this function to it, and the system will take care of actually taking the new tweets for that user. In this case, the user is the key, and take the new data of that user, apply the function on the previous state, and get the new state. And the system will continuously do this operation over and over again underneath. So it's pretty easy to plug in arbitrary stateful computations in this model. Yes. What goes underneath? So underneath, essentially, this computation essentially boils down to a number of joins happening on every batch, where the new data is partitioned based on the key, and the existing state is, which is also an RDD kept in the memory, is partitioned based on the same key and joined together to combine them, to combine the new state, the old state, the new tweets, and generate the new state. Now, regarding how it happens, occurs underneath, you can actually look at the source code. It's not too complex a source code to look at it, but I can talk about it offline on what are the implications of that. Let me move on. The third thing that I want to discuss, highlight in the DStream API, is that you can, there's this operation called transform, which gives you access to every RDD in the DStream directly. And you can apply any RDD to RDD transformation on each RDD of a DStream. And this essentially allows you to intermix arbitrary batch-like computation with streaming-like computations. For example, let's say you have the tweet stream, and you want to essentially filter out tweets that have some spam hashtag in it. And to do that, you have a file in HDFS which has all the spam hashtags, and you want to take the stream and join it with the file. And that you can do very easily using this transform function as shown, where you basically define the function that for every tweets RDD from the tweets DStream, I'm going to join it with this spam file and filter out the results after the join. And so this and this allows you to basically view the stream both sometimes as a point of view of a stream, or sometimes as the point of view of pure sequence of RDDs, and you can do arbitrary RDD computations on top of it. And this duality of DStream and RDDs gives you a lot of power. For example, you can combine live data stream with historical data. Let's say you have some historical data and you have computed data models with it by running Spark jobs on it. You can take the data model that you have learned and apply it on a live data stream, just like the way I've shown spam hashtags being used to filter out live data stream. You can combine streaming with arbitrary machine learning and graphics and all these algorithms that are also come as parts of Spark. So you can do offline learning and then online prediction. You can also do online learning and prediction using this transform. Then you can also query streaming data using SQL. So and to show this, to show how that can be done, I'm going to refer to the Databricks Keynote demo. So how many people here actually have seen the Databricks Keynote demo that we showed yesterday? Okay, I'm guessing most of you. So just for those who have not seen the Keynote demo, what we had shown is how using the Databricks product we can actually take the stream and a live Twitter stream, and we can apply machine learning algorithms on top of it, and then also apply SQL queries on top of it. And what I'm going to do is essentially show the code, the simple code that was running as part of the demo. And so what we had done essentially is create a new streaming context and also a SQL context that Michael talked about. Create a Twitter stream, apply a filter to filter out only English streams, English tweets, apply a window operation on it. And essentially what we did after that is that for each of the RDD, we registered the RDD as a table in the SQL context. And so as the DStream was running, last 1 minute of tweets was essentially registered as a ever-changing table in the SQL context, and which allowed us to then finally run SQL queries on the last 60 seconds of data. And that essentially was the magic that you can do on the open source right now, minus the visualizations and stuff. So this shows how easy it is to combine different of the components for having with streaming and Spark SQL all of it together. Moving on, the last but not the least, the big advantage of having this unified stack is that you can do combined interactive batch and all of the together without having to change the code. You can figure out stuff interactively, write a Spark program to do it on much larger amount of data, and pretty much the same amount of very similarly looking code you can plug it in a using and use DStreams to get real time data processing right out of the box. Finally, a small point about the fault tolerance. The way we handle fault tolerance to give you stronger guarantees than what other systems can give is that the raw input data is actually replicated in Spark's memory. And so what allows us to do is that if any of the worker node dies, so the data is replicated, if any of the worker node dies, since the data is replicated on at least 2 machines, we can recompute automatically the transform data, in this case, let's say the hashtags that was lost, recomputed back again from the raw input data. And so your computation will never be affected by any failure of any of the workers. And as a result, all the transformations that we do, counting everything, have exactly one's property, no matter there is a worker failure or not. Out of the box, we provide these. Oh, here's a question. That's a good question. We have exactly one's properties for any data transformations. If you're pushing the data out to a database or some arbitrary database, then you have to make sure to get exactly one's properties by doing idempotent updates to the database. That's a good question, Remy. Anyway, so out of the box, we get input sources of Kafka, Flume, Akka actors, raw TCP sockets, plain old HDFS, and Twitter, of course. But it's very easy to write your own custom receiver. There's a very simple receiver API where all you need to specify is what to do when the receiver is started and what to do when the receiver is stopped. And that's it. So people have been writing their own receivers using that API. And also for testing, if you may not have a data stream source, but you may want to test your streaming program with arbitrary data. So you can generate your own sequence of RDDs from, let's say, some offline log files and push them down a streaming program as if it's a stream. So that can also be done using something called a queue stream. So that is very beneficial while testing. Anyways, to wrap up, where are we going in the future? So in future, we are planning for better, tighter integration between with SQL, with MLlib. We were planning for having online prediction algorithms right out of the box in MLlib. Graphics, Ankur later might talk about it. We also have planning further improved integration with different sources like Amazon Kinesis, etc. Improved control over data rates so that you can control your streaming program a lot better, and of course Python API, which I touched upon earlier. Anyways, one thing to note about today's tutorial. So in today's tutorial, we're going to process Twitter data stream to find most popular hashtags over a window. But for this, you need to actually provide a Twitter account because that's only way to access the Twitter data stream. So for that, you need to set up a few keys. All the instructions are given in the tutorial. But the thing to keep in mind is that you will not have to enter your password anywhere for the tutorial. You just have to enter the keys, and once your tutorial is over, you can easily delete off all the keys, and your account will never be compromised. So if you're ever concerned while seeing the web page that, whoa, whether I'm entering my Twitter, what's gonna happen? You don't have to worry. You can delete off the keys, and your account will be safe. Finally, to conclude, I have not covered a lot of the finer things like performance tuning, etc. You can always go to our streaming programming guide to get all those details. And obviously, you can ask questions. I'll be around. So, yes, one question. JMS connector, no, there isn't a JMS connector, JMS receiver yet, but I have heard people that they have written it. I just don't have the source code. but people have written it. Yeah. Yeah. Okay. We're running out of time, so we can let's have all the questions offline. You'll find me around, so just ask me.